Hi everybody, it's your human anatomy and physiology teacher, Mr. Poser. Today we are continuing our second unit on the introduction to the human body with a video on homeostasis, the great balancing act. Homeostasis, if I were to put it in a few words, would be that it's your body's way of maintaining a normal state within you, as opposed to a constantly dynamic changing outside environment. One of your body's main jobs is to maintain homeostasis, which is a stable internal environment. And why is it called the Great Balancing Act? And why do we have this lady with the umbrella on a tightrope? Well, because she's balancing. All right. So imagine you being on a balance beam, or maybe even on a tightrope if you're that athletic enough. If you're on a balance beam, let's just say, and you start to feel your weight shift to the left, what might you do? Well, you might twist all the way over to the right to compensate for the fact that you are already turning to the left in an attempt to stay on the balance beam. Or, well, maybe overcompensated by going to the right, so then you shift back to the left again. But either way, what you are trying to do is correct the changes in the balance that your body has made so that you can stay right in the middle. And homeostasis is kind of similar to that. So a balance beam, it really isn't that far off of a comparison when it comes to homeostasis. So what is it exactly? It describes the ability, as I said, to maintain a relatively stable internal condition even though the outside world is changing. It's a state of equilibrium or balance. You may have heard me say this before, but any cause of death that's ever occurred to any living thing ever is a result of an irreversible loss of homeostasis. So this is your body's way, one of your body's ways of keeping you alive, right? Although the outside temperature might be different, the air pressure might be different, there's different stimuli coming at you at every single moment, your body is able to maintain a relatively stable environment thanks to its ability to maintain homeostasis via a mechanism called a feedback loop. And we're about to dissect what a feedback loop is here in just a minute. But homeostasis is equilibrium or balance. It's your body's ability to maintain that. And once it's lost, it's gone forever. All right. So the body in balance, what are some variables that might be maintained by homeostasis? So what are some things that your body needs to keep constant in order for you to stay alive? I bet you can think of a few. I have a list on the next page that we're going to look at. But if you can think of a few, pause this video, try to guess what are some variables maintained by homeostasis, and then we'll move on. Pause it. Okay, let's go. Hopefully you pause the video. So some examples of some variables that need to be at a constant rate and thus maintained by homeostasis are temperature. Even though it might be like 92 degrees outside right now, your body needs to maintain a constant internal temperature in order for everything to be working properly. Blood pH. Your blood can't be too acidic. It can't be too basic. It needs to be neutral. It needs to be right at 7 for a pH. Your body works hard to maintain its pH balance. Your blood sugar. This is a big one. People that with type 1 or type 2 diabetes are unable to control their blood sugar. So we're going to talk about type 2 diabetes quite a bit. On account of the fact that they are not producing insulin, or their insulin does not get picked up by their cells. They cannot control how much glucose is in their blood at any given time. Water balance. Okay, your cells, we talked about this in the last unit, your cells need to stay at an isotonic solution. They need to stay in isotonic equilibrium. So they're not losing too much water, they're not gaining too much water. This is maintained primarily by your urinary system. That's another example of homeostasis. Blood pressure. If your blood pressure is too high, it can cause tears in your blood vessels and then cause clots. If your blood pressure is too low, then blood might not be able to reach certain areas of your body in time. Like, say, for example, if your blood pressure is too low, you get up really fast, blood's not going to reach your brain in time, and you're going to pass out. It's happened to me. Maybe I shouldn't be sharing that, but still. And then ion balance. All right, so ion balance is also extremely important when it comes to, say, neuron function. It comes to muscle function. All of these factors need to be maintained and kept stable by an internal environment, or for the internal environment. All right, so the main way that your body maintains homeostasis is through what we call a feedback loop. And there's three main parts to a feedback loop, or three components of control, as we call them. One are receptors, one's what we call a control center, and the third is what we call an effector. Here's a loop, a very, very extremely generalized feedback loop down here. So there's two other terms that I have not defined yet. A stimulus is a change in an internal environment. That stimulus, or this change in the internal environment, is picked up, the message is received by what we call receptors, hence they receive it, right? Receptors are able to communicate with the control center, and the control center establishes a set point, which means that, hey, are things messed up or are they not messed up? And when they are messed up, what the control center can do is send a signal or some kind of communication with the effectors, and the effectors go about making a change and producing a response to correct the change that happened in the first place. We're going to talk about this when it comes to body temperature in just a moment here. All right, so as I said, the receptors, what they're going to do is they're going to monitor the environment and respond to changes within the internal environment. So particular organs detect a stimulus, and a stimulus is a change. All right, so what the example that we're going to be using of a negative feedback loop to illustrate homeostasis is regulating body temperature on a cold day. All right, so you're outside. It's cold. It's December. It's August right now, but it's December, okay? What happens is just the stimulus occurs first, and your blood and skin temperatures fall after you've been outside for a long time. This is not sustainable. Your body is thus not at homeostasis if your body temperature is too low. So a receptor, possibly in your skin or in your muscles, temperature receptors detect changes to the internal body temperature, and they're able to send nerve impulses, thanks to the action of the nervous system, to the brain. All right, so they say, hey, it's cold, and then they send a message to the brain, which it serves as what we call the control center. And here's our little shivering gnome over here in case you needed to see him. The control center determines, as I said before, the set point at which the variable is maintained. It's a self-check and receives the messages. All right, so the receptors have sent a message to the brain saying, hey, I'm cold. And what does the brain do? Well, particularly a part of the brain called the hypothalamus is stimulated by that message that it receives, and it sends nerve impulses to other relevant parts of the body. All right. So what we're referring to as the set point, you might know this from before or from previous knowledge, but your body really typically tries to maintain a temperature anywhere between 96 and 99. All right. A lot of times it's like 98.6, but it's not always. It's more variable than that. But the point is, your brain has a set point. It should say, hey, body temperature should be at this temperature in order for everything to be functioning properly. All right? And if the receptors send a message to the brain and the brain figures out, oh, hey, we're below the set point, we're below the body temperature that we're supposed to be at, then the brain's going to do something about that. It's going to send a signal back to the body, except it's going to be to the relevant organs that can warm us up and reverse the change. And what those organs are called, they're called the regulators, or more commonly known as the effectors. And the effectors provide the means to the stimuli. So it's what we call a corrective mechanism, right? So once this message is sent out by the brain, where might it go in order to increase body temperature and bring us back to the set point? Well, it might send it to your muscles, and your muscles might start to contract rapidly. That's called shivering. Shivering produces a lot of heat. In fact, your brain might send some messages to the smooth muscles surrounding your blood vessels, okay? Allowing more blood, restricting blood vessels. Restricting blood vessels, reducing the blood flow to the skin to try and keep heat inside. Okay, so your skin is going to be the first thing that becomes cold, and your body is going to try and keep the warm blood closer to your internal organs, which are keeping you alive. But anyway, the corrective mechanism, it's a decrease in heat loss and an increase in heat production. So it's going to work in this way to keep us warm and keep us at the set point. And then as it says here, shivering will occur when insufficient heat is produced. Okay, so there it is. Your body's going to try and bring us back to the set point. So what we just walked through is called a negative feedback loop. And you're like, hey, negative, that's a bad thing. But it's not a bad thing. In fact, a negative feedback loop is the primary way that your body is able to maintain homeostasis. So we're going to talk about the two different types of feedback loops before we end up this video. And look at, as I said in the first video in this unit, I did not make this flip chart. So it took me a while to figure out why Toucan Sam was here. It's because Fruit Loops, and we're talking about feedback loops. Boom, right? Anyway, feedback loops compare current conditions to set ranges, and we have a positive feedback loop and a negative feedback loop. The example that we just walked through is a negative feedback loop. And it's called a negative feedback loop because if there's a change into the internal environment, a negative feedback loop will stop or decrease the change. Or a word I like to use, it will negate the change. It will work in a way to act against whatever change was made. So, to our example from before, if you get cold, a negative feedback loop will help you become warm to reverse the change that happened. You became cold, then it's going to warm you up. The opposite is true with regards to body temperature. Take a look at this picture down here. If body temperature increases, it's a very, very hot day and you're wearing like 4 hoodies or something like that, what's going to happen? Well, cooling mechanisms are going to activate. You're going to get more blood flow to your skin to try and get rid of some of that heat. You're going to sweat to try and cool yourself down. All right? But it's the same thing. You get too hot, the negative feedback loop will reverse the change and try to cool you down. Okay? So the negative feedback loop does whatever the opposite of the stimulus is. Okay? Your blood sugar spikes. You drink 4 Mountain Dews in 20 minutes. Okay? Your body will work in such a way to lower the blood sugar. Or if you've been fasting for a week, okay, your body will try, and you have very low blood sugar, your body will try to increase your blood sugar. All right, so it reduces or reverses or negates the change that happened. All right, but a positive feedback loop, you're like, why would we ever need a positive feedback loop? Well, it's very necessary for some purposes. A positive feedback loop will increase a change that's happened to your internal environment. So let me walk you through a few examples here. An example is a torn blood vessel that stimulates the release of clotting factors. So take a look at this. Imagine you're bleeding. All right, you tore a blood vessel and there's blood coming out. Oh no, what's going to happen? Well, you're going to stop bleeding unless you're a hemophiliac. Why are you going to stop bleeding? Well, certain factors in your blood that are called platelets, what they're going to do is they're going to collect near the blood vessel, okay, and they're going to try and form a plug. But not only do they do that, what the platelets do is they form a plug at the tear, okay, they start to form a clot, but then they also send out other signals they're called clotting factors to the rest of, the platelets in the blood, right? So it's going to send out a signal that will communicate to these cells called platelets that will also come to the clot. Okay, like they form the clot. They say, "Hey, come help us form this clot." Okay, and then more platelets come, and then those platelets say, "Hey, help us form this clot." So what's happening is it's amplifying the change. Okay, it's like I've referred to it many times as a vicious cycle. Right? One change causes more of the same change. Right? Another example of a positive feedback loop is actually during childbirth. So when the baby decides to push through the cervix and start to come down, or puts pressure on the cervix to try and open, and so that it can go through the birth canal. The expansion of the uterus and the expansion and the pressure on that cervix is going to release a hormone called oxytocin. And oxytocin, what that's going to do is going to trigger to expand the uterus and expand the cervix to get your 8-pound parasite out of your body, right? And what does that do? Well, it causes more of that change. It's going to repeat and repeat. So the uterus and the birth canal and the cervix will get wider and wider, 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 wider until you can get that 8-pound bowling ball parasite out of you. So that is a positive feedback loop. It works to amplify a change that's happened within the body, right? You got clotting factors in your blood. More platelets are going to collect, and more clotting factors are going to collect to stop the bleeding. You're having a baby. Well, the expansion of the uterus and the cervix is going to cause more expansion of the cervix and the uterus. All right, so that's a positive feedback loop. I believe that's it for this lesson. Let me double check here. Yes, it is. All right. Let me know if you have any questions. I'm sorry if I rambled here. Have a good one. Bye.